loves to disconnect on me. All right, so let's discuss. All right. So again, the reason I gave you guys these questions is because I knew you were going to struggle on them. All right. So let's start with a radical equation. Now, this is a particularly harder radical equation, but we did talk about this yesterday when y'all did that warm up from yesterday. So I wanted to see if you remembered what I told you how to do. All right. So let's just walk through this together. Someone raise their hand and tell me what they think the first step is. So just take a shot in the dark. What do you think? Square both sides. Now, we know how to handle the right side because the square root and the square just cancel out. So this would be x minus 8 on the right. But what did I say you have to do with the left side yesterday? Nope. We have to box method it. All right. This is the same thing as the square root of x minus 2 times the square root of x minus 2. So we can't just square the square root of x and square the 2 individually. We actually have to do a quick box method. So if I put it in a box, I have square root of x minus 2, square root of x minus 2. What's the square root of x times the square root of x? Just x. What's negative 2 times the square root of x? Negative 2 square root x. This is the same thing, so negative 2 square root x. What's negative 2 times negative 2? Positive 4. So now I'm going to pull everything out and combine like terms, which my like terms, remember, if they have the same radical and index, or radicand and index, you can combine the like terms. So this would be x, and then what's the next part? Plus 4. All right. Now, what do you guys think my next step is going to be? We're going to subtract 4 to both sides. I get x minus 4 square root x is equal to x minus 12. What am I going to do next? I can subtract the x to both sides. So the x goes away. So I have negative 4 square root x is equal to negative 12. Next step, I can divide by negative 4. So that's square root of x is equal to 3. What's my last step? Square both sides. That goes away. X is equal to 9. Now, you still need to do a quick check and make sure that it works. So if I just plug it in real quickly, the square root of 9 is 3. 3 minus 2 is 1. 9 minus 8 is 1. Square root of 1 is 1. It works. So x equals 9 is your answer. So guys, in reality, these aren't particularly hard. It's just taking a skill that you already know how to do and applying it in a different context. All right, you guys saw these when we were doing quadratics. All right, you saw how to expand perfect square trinomials. It's essentially the same thing, but it's with square roots instead of x squareds. All right, any questions on number 1? All right, number 2. All right, so this one is a fractional exponent. So I'm not going to convert it to a radical. We're going to leave it as a fractional exponent. But what do you think my first step would be to solve? Subtract the 11. I get 3x to the 3/8 is equal to 24. Next up, divide by 3. X to the 3/8 is equal to 8. Now, what did I tell you you have to do or raise your exponent to get rid of a fractional exponent? The reciprocal. So I'm going to raise both sides to the what power? 8 over 3. So that goes away, cancels out. So x is equal to. Now, again, you can put that in your calculator, but if you want to do it using kind of mental math, you can think about it this way. You take the cube root of 8, and then you raise it to the 8th power. What's the cube root of 8? 2. If I raise it to the 8th power, what do you think? 256. So x is equal to 256. I can assure you if you plugged it back in, it'll work. Any questions on the equation side of things? All right. Now to the simplifying, which this is probably where y'all were struggling a little bit. Now, I purposely picked some with stuff outside of the radical because what did I tell you yesterday you have to do when you start bringing stuff outside the radical, but there's already something out there? So, like, for example, we know the 9's a perfect square. So what's going to go on the outside? 3. So this would be 3x cubed y. Why did I bring that down? It's already there, but technically we have to do what? Multiply it together. All right. Now, x to the 5th. Remember, you want the closest multiple of 2 and then whatever's left over. So what's the closest multiple of 2? x4, which leaves me what left over? X. So if I take the square root of x to the 4th, what is that? X squared. So I get 3x squared times x cubed y. Then I have x y to the 4th. Why am I multiplying the x squared to the x cubed? Because you have to. That x cubed doesn't just go away. All right. Then we do the same thing for y to the 4th. Is y to the 4th a perfect square? Yeah. So you can just take a square root of that, which is what? Y squared. So this would be 3x squared times x cubed times y squared times y. What's the only thing I have left under the radical? X. So if I clean up the outside a bit, so I need to multiply these like bases together. I would get 3x to the what? 5th. Add them. All right, it's not a power rule, it's just products. So you just add them. Y the what? 3rd. 2 plus 1. Square root x. Any questions on number 3? All right, number 4. So remember what I said. I just say take it one step at a time, do one part of under the radical at a time. So I'm going to start with the 150. Now, a lot of you I saw doing the prime factor method. So I'm going to show you guys that one. So what's 2 factors I can break 150 down into? 15 and 10. Neither of those are prime, so I need to break them down again. So 5 and 2 for 10. What about for 15? 3 and 5. Now, since I'm taking a square root, how many of each number repeating am I looking for? 2. What's my group of 2? Right. So if you look at all of your prime factors to the bottom of your branches, you're looking for the one that repeats, which is this one. And remember, we only bring one of those out because if I multiplied 5 times 5 together, what would that be? 25. All right. So here's what I recommend. Whenever you're doing this, if kind of the factor tree throws you off, you can always rewrite it using multiplication. So in other words, you multiply back your pairs to put under the radical. So this would be 25 times, then you take whatever's left over. So this is what's left over. So I'm going to multiply those two together. 6. And then x squared y to the 7th. And you got the 2x cubed on the outside. 3 times 2. So you're multiplying the factors that are left over. All right, so we found our perfect square, which is the red. So the red is our perfect square. The green is what's left over. So if I take the square root of 25, what do I get? 5. So if I bring it out to the outside, what will be the new coefficient on the outside? 10x thirds. So this would be 5 times 2, x cubed. So that would be 10. And I'll simplify that in a second. And then we got 6, x squared, y to the 7th, still under the radical. Now we know the 6 can't simplify any further because we already did the numerical one. So now we're moving on to the x squared. Is x squared a perfect square? Yeah, it's an even exponent. So I can just square root it. So what's the square root of x squared? X. This would be 5 times 2 times x cubed times x. And I have 6y to the 7th. Y to the 7th. How's this break down? Y to the 6 and y. So what's the square root of y to the 6? Just divide it by 3. Not 2. Not 3. Divide by 2. Y cubed. So this would be 5 times 2 times x cubed times x times y cubed 6, and then I only have one y left over. So my radical's all simplified. I just need to clean up the outside. So what will my final answer be if I clean up the outside? 10x to the 4th y cubed square root 6y. So guys, these aren't necessarily hard. They're just dicey. All right. There's a lot of numbers being thrown around. You got to know like what parts you're using, what parts you're not using, what goes under the radical, what comes out. All right. So for me, I've done this so often, I can skip like 5 of these steps. But if this step, especially with the numerical part, if that's what makes you comfortable, do it. All right. Take as many steps as you need. You don't need to shorthand it. All right, especially if this is stuff that confuses you. All right, any questions on that? All right, now adding and subtracting radicals. So when we're adding and subtracting radicals, it's the same thing as combining like terms. So what did I say yesterday that you need to do if you do not have the same radicand underneath? So radicand's the what? So we can't just divide them by 7 because that won't work because of the square roots. But we can simplify the square roots. All right. So if I simplify the square roots, we'll start with the first one. So let's start with 63. Two values of 63. 7 and 9. 7's prime, 9's not. 9 I can break down into what? 3 and 3. So, what's my pair? Which of those circled values is my pair? 3 and 3. So, if I multiply 3 times 3 back, I get 9 times 7 x cubed. All right. Which, what's the square root of 9? 3. So this would be 3 square root 7. And then x cubed, how do I break it down? X squared and x. So what's the square root of x squared? X. So this would be a 3x and then 7x. All right, and we're done with the first one. The second one, 28. Yes.
If it's square root, how would you get the cube out of the x?
The what, huh?
If it's square root, how would you never mind.
The 3 or the... Okay. All right, 28. Two values of 28. 7 and 4. All right. Now, 7's prime again. I make a habit of circling my prime numbers so I know where the end of my branches are, because if it's prime, that's the end of your branches. All right. 4 we can break down to 2 and 2. Both are prime. So, what is my pair? 2. So, I'm going to rewrite it with the 4 in mind. I'm just going to multiply the 2 by 2 back together because it's still under the radical. So, I have 4 times 7, because I'm bringing out what's left over, x. So, square root of 4? 2. So, this will be plus 2 times x, square root of 7x. And x is not a perfect square. There's nothing we can take out of it. So we're done with that. Now, will I be able to add my coefficients together? Yeah, because we have the same radicand. So now all I got to do is just add the 2x and the 3x and then slap a square root of 7x on that at the end. So our final answer is going to contain the square root of 7x. But what's the coefficient that goes in front of it? 5x. All right. Any questions? Do I need to do number 6? It's really similar to number 5. Speak now, forever hold your peace. All right. Okay, 20. We're going to simplify that first. 2 factors of 20. I'm going to use 2 and 10. 2 is prime. Break down 10 to 2 and 5. Both of those are prime. What's my pair? 2 and 2. Multiply them back together, I get 4. So this means negative x cubed, square root of 4 times 5. So, what's the square root of 4? 2. So this would be negative 2x cubed, square root of 5. Now, the second radical, what's the only part that I'm going to have to square root? The x squared. Because the 5, we just can't do anything because it's prime. So what's the square root of x squared? X. So if I bring it out, I'm multiplying. This would be negative 3x squared times x square root of 5. So that would be what? Negative 3x to the what? Cubed square root of 5. Now I got the same radicand, so I can add the two coefficients. So my final answer is going to contain the square root of 5. So what goes in front of it? Negative 5x cubed. Any questions? All right, 7. So we did one similar to this yesterday, and we actually did one within, like, similar to it in number 1, because this is the same thing as 2 minus x square root 6 times 2 minus x square root 6. So what am I doing? Box method. So if I make my box, I have 2 minus x square root 6, 2 minus x square root 6. All right, what's 2 times 2? 4. 2 times negative x square root 6? Negative 2x square root 6. This is the same thing. Now, think about this carefully. Coefficients by coefficients, radicals by radicals. All right? So, if I do negative x times negative x, what's that? X squared. If I do square root 6 times square root 6, what's that? Square root 36, or just 6. This would be 6x squared. Then I just pull it out, combine like terms. So my only like terms are right here. This would be 4 minus 2x plus negative 2x minus 2x is still negative 4x square root 6 plus 6x squared. And that's it. There's no extra simplifying. There's no factoring. They just want us to multiply it. Any questions on that one? All right, last one. Same thing, box method. But we had one like this yesterday. What do you think the outcome is going to look like? It's a difference of 2 squares. So our outcome, our square root part's probably going to cancel out. 7 times 7. We got 7 square root 6, negative 7 square root 6. Square root 6 times negative square root 6. Not 6i. Negatives on the outside. Negative square root 36, which is what? Negative 6. Because it would be negative square root 36. Negatives on the outside. If it was on the inside, then we take an I out. So if I combine like terms right here, what happens to those two? They cancel. So this would be 49 minus 6, which is just what? 43. So guys, these are not necessarily hard. They're just tedious. All right. So like I said, if these are like something that kind of is complicated for you, don't shorthand stuff. Don't skip steps. All right. So go ahead and take out your packet. I want to pick up with where we left off yesterday. So I'm on page 26. I want to finish the last little bit of 5.5. So page 26, looking at number 4. So yesterday we had a bit of a conundrum. All right, because we were rationalizing a denominator. But when we did it like we would a square root, and we did it a couple times, we still kind of ended up with the same thing. Now, I did this on purpose because I wanted to see if you guys could figure out what I actually needed to do. So think about this logically. If a square root, when you're rationalizing a square root, you got to multiply it by that square root twice. All right? With a cube root, what do you think you're going to have to do?
Three times.
3 times. So, just like the square root of 3 times the square root of 3 is 3, the cube root of 3 times the cube root of 3 times the cube root of 3 is 3. All right? Because this is the same as the square root of 3 all squared. This is the same as the cube root of 3 all cubed. All right? So, now we could multiply cube root of 9 3 times, but that would give us like really big numbers. However, what could I multiply to the cube root of 9? So something with a cube root that would give me a perfect cube underneath that radical. So think about what your perfect cubes are. What could I possibly multiply under that radical? The cube root of 3. So the cube root of 9 is technically the same thing as the cube root of 3 times the cube root of 3. So in other words, this is the cube root of 3 squared. But we still need to add another cube root. So I wouldn't erase what we wrote here. I would just put a line through it saying, okay, that's not what we wanted. And that's okay. So I'm just going to rewrite it down here. I'm going to multiply this by the cube root of 3 over the cube root of 3. So this would be the cube root of 3 over the cube root of 27. Because we just multiply what's under the radical, so 9 times 3. What's the cube root of 27? 3. So we got the cube root of 3 over 3. And just like that, our radical's gone. So this is just something you got to think about. You could have multiplied. So if you couldn't find that perfect cube, you could have just bit the bullet and multiplied the cube root of 9 twice. Like in a row. So the cube root of 9 times the cube root of 9, cube root of 9. Because then those 3 would cancel out. So just be 9 on the bottom. You get the cube root of 81 on top, but then you'd have to simplify it down. You still get the same thing. All right. The easier way is just finding out which number you can multiply to give you a perfect cube. All right. Now, most of them, when I ask you to rationalize the denominator, it's mainly going to be squares, so square roots, but it is interesting to look at it from a cube root perspective. All right. Now, the last one. All right. So, with the bottom one, what is going to happen is that, what do you notice about the denominators in the last two examples? Well, they got the square root, but what's going on with it? You're adding or subtracting a whole number to it. All right, so in other words, it's almost like you have a binomial on the bottom. So, we've already done a couple like this, but if I want to completely get rid of a square root, what form of advanced multiplication? So if you look back up here, what form of advanced multiplication gave me an expression with no square roots? So those four examples, there's one of them that completely got rid of the square roots. Which one? The difference of squares one. So with 5 and 6, you have to multiply both the numerator and the denominator by the opposite of the denominator. And what I mean by that is think difference of squares. All right. So in other words, for number 5, what do you think I'm going to multiply to the top and the bottom? 2 plus the square root of 5. Because what will happen is that the square roots will end up canceling out, at least in the denominator, which is what we want. All right. So let's work through this. So I don't really need to do a box method because all I need to know is that these two would square and these two would square. All right, you just got to remember to make sure the negative's there. So what's 2 times 2? 4. Negative square root 5 times square root 5. Negative 5. And again, the reason I did that, because if I did do that quick box, which you don't have to write this down if you don't want to, but let's say I did it. I have 2 minus square root 5, 2 plus square root 5, 4, negative 2 square root 5, positive 2 square root 5, negative 5. These two terms would cancel out. So in reality, we don't need to worry about that middle term because it'll end up canceling out anyway. So that's kind of a way you can shorthand it. Now, the 6 times the 2 plus the square root of 5, you just need to distribute. So what's 6 times 2? 12 plus, what goes on the outside? The square root of 5? 6 square root 5. So this would be, if I simplify stuff down, 12 plus 6 square root 5 divided by negative 1. Now, if I divide by negative 1, what's the only thing that's going to happen to the numerator? Both the signs change. So my final answer would be negative 12 minus 6 square root 5. So whenever you have a whole number being added or subtracted by a root in the denominator, think about difference of squares. That's what you would multiply to get rid of it. All right, look at number 6. Last one, at least for 5.5. All right. So for number 6, look at the bottom. What do you think I want to multiply the top and the bottom by? 3 minus the square root of 7. So the denominator, remember, you can just multiply 3 times 3 and then multiply square root of 7 by negative square root 7. So what would be in the denominator of my answer? So what's 3 times 3? 9. What's square root 7 times negative square root 7? Negative 7. Now, the top part, you would have to do a box method. All right. So if I do a quick box over here, this will be 5 minus the square root of 7, 3 minus the square root of 7. 3 times 5? 15. Then negative 3 square root 7, negative 5 square root 7. Negative square root 7 times negative square root 7? Positive 7. So if I pull everything out and combine like terms, my like terms are here and here. So what's 15 plus 7? 22 minus what? 8 square root 7. Do a little simplifying. This would be 22 minus 8 square root 7 all over 2. Now, do you guys remember when we did the quadratic formula stuff and we were having to simplify that? Can I simplify that expression any? Yeah, you can. This is the exact same thing as 22 over 2 minus 8 square root 7 over 2. So what will my final answer be? 11 minus 4 square root 7. Any questions on that? All right, so that's enough with operations. All right, any questions on 5.5? All right, so what I actually wanted to get into today, but I really did want to hit again on the operation stuff because I felt like yesterday y'all were like, what in the wide world of sports is this? So I had to do some extra practice with that, but we still need to keep on trucking. So now we are going to look at lesson 5.6. So I'm on page 28. So now we're going to look at graphing square root and cube root functions. All right. So the only two graphs that we're going to care about right now is square root graphs and cube root graphs. All right. Now, something that's interesting about square root graphs and cube root graphs is that it almost looks very similar to their inverse graph. So, what do I mean by the word inverse? What does inverse mean? Opposite. So, if I'm graphing the square root of x, what would its opposite graph be? X what? What's the opposite of square root? Squared. So the inverse graph of square root of x would be x squared, or a quadratic graph. What about cube root? What do you think the opposite or inverse graph would be? X cubed. All right. So what we're going to do first is we're going to graph our graphs by hand first. So first off, square root of x. All right. Remember, we don't want imaginary numbers. So what's the lowest number that I can have under that radical and plug in for x? So in other words, that lowest number under the radical, what's the lowest number I can plug in for x and not get an imaginary number? 0. Square root of 0 is 0. All right. So I cannot go any lower than the square root of 0. So I'm going to start with 0. All right. So if I do 0, what's the square root of 0? 0. I'll do 1 next. Square root of 1? 1. Now, I want to, because I don't want to get any weird numbers, I want to keep with perfect squares. So what do you think my next x value should be? 4, which is 2. And one more. 9, which is 3. So I'm going to go ahead and graph those 4 points. So I got 0, 0, 1, 1, 4, 2, and 9, 3. So my graph looks a little like this. So in other words, it looks like half of a parabola turned sideways. So pattern-wise, all right, is that it's kind of the opposite of the quadratic pattern. So, do you guys really care about the pattern, or would you rather just do tables and keep it safe? It's up to you. All right. But for those of you who do like the pattern, it's kind of the opposite. So, whatever vertical distance you go out from 0, all right, or its vertex, because this is considered its vertex, you would then, to get the horizontal distance, square it. So whatever the vertical distance is, we're going to square it to get the horizontal distance. So for example, if I go 2 up, square it, I'll go 4 out. All right. Now, what do you think the domain of my graph is? So the domain, what's my lowest x value? 0. And where does it go to? Infinity. It goes on forever to the right. What about my range? What's my lowest y value? Nope. 0. If you look, I have nothing in the negative y's at all. I don't have y's start until I'm at 0. So it's from 0 to negative infinity, or positive infinity. Now, if I look at x cubed now, not x cubed, cube root. All right. Now, remember what I said with cube roots. What's so special about cube roots? Can we have a negative under that radical? Yes. When it comes to taking cube roots, there's no way you can get an imaginary number. All right. You're always going to get a real number with a cube root. All right. So that means that I can go all around wherever I want. I can get into the negative x's, I can get positive x's. All right. But I'm still going to put 0 in the middle. All right. Because if you think about it, cube root of 0, and then you'll start seeing stuff repeating. So I'm going to do the positive sides first. So what's the cube root of 0? 0. All right. Cube root of 1. 1. What's my next cube root? Or my next perfect cube? 8. What's the cube root of 8? 2. Now, I'm going to go the negative side. So what's my next perfect cube after less than 0? Negative 1. What's the cube root of negative 1? Not 1. Negative 1. What's my next cube root? Negative 8. And what is it? Negative 2. So what do you notice What happened? They're not necessarily symmetrical, but what happened? Didn't they flip signs around the vertex? Yeah. So if I graph this, I would have 0, 1, 8, 2, and then -1, -1, 8, -2. So my graph would look something like this. All right. Now, pattern-wise, I don't really want to explain the pattern for this one because it's weird. So we're just going to kind of bypass that. I say if I give you one to graph, make a table. All right. But domain-wise, what's going on domain? It's all real numbers. Since there's arrows on both the left and right side of my x's, it's all real numbers. So you can either write it as -infinity to infinity, or you can write it as the capital R with a line through it, or you could basically write all real numbers. What about the range? It's also all real numbers. So even though it's going up very, very, very slowly, all right, it's still going up. All right. It's just there's not a big rate of change with the graph. So it's still all real numbers. Now, let's describe the rate of change for the square root function and the cube root function. Well, square root. So with the square root function, so rate of change, when I say rate of change, I'm talking about how fast it's going up or down. What's true about the square root function? Is it going up pretty fast? Which means, are the y values getting bigger very quickly? No. All right. In fact, it takes a while for them to get up there. All right. Like you got to have x values like in the thousands before you even hit about, somewhere in the 20s. Okay. So, in other words, the rate of change, I don't know why I wrote root, but you know what? So, the rate of change is very slow. Because parabolas, we're used to it getting bigger y values very quickly. Linear functions, we're used to it increasing, not necessarily super quick, but relatively quick. Exponential, they grow really quick. But square root does not. It still grows, it's just more at a snail's pace. Now, just so you're aware, these two are the parent functions for their respective type. So square root of x is the parent function for a square root. Cube root of x is the parent function for a cube root graph. Now, we talked about parent functions back in your quadratics unit, so like unit 3. Does anyone remember what I meant by parent function? It's the what? It's the original. So in other words, any other square root function, we're doing some form of transformation to this square root function. All right. Any cube root function, we're doing some form of transformation to the original cube root function. These are the originals. Now, why am I bringing that up? Let's look at the next page. So, quick review on function transformations. We briefly talked about this back in Unit 3. And you also saw it when we did our transformations unit way back at the beginning of the semester. So, If I'm adding something outside of the parentheses, so think back to your transformation unit. What does that mean I'm technically doing? What type of transformation? So is it going to be a translation, rotation, reflection, dilation? What do you think? So I'm adding a value outside of my function. It's a translation. Am I going up, down, left, right? Up. So this is a shift up. So with this function right here, if you look, I'm adding 5 and it's not under the radical. So I call this outside the brackets. All right, your bracket being your radical. What's it going to look like in comparison to the original function? It's going to be what units? Up 5 units. What if you're subtracting something outside of its bracket? You're going to shift down. So here, the cube root function, we're subtracting an 8 on the outside of the radical. So we're going down 8 units. Now, what about if it is inside the bracket, so it's under the radical? And think about this carefully. So my suggestion is think about vertex form. Not right. It's actually left. So just like how we had x plus, not x, x minus h squared plus k, where k is your vertical transformation and h is your horizontal transformation or translation. Since the minus is originally there, and that's true for a square root function, a square root function would be square root of x minus h plus k. All right, just with a square root instead of a radical, or radical instead of a square. Oh my gosh, I can't English today. But because the minus is already there, this is talking about right. So if it's a plus, you're talking about you're shifting left. So this would be left 2 units. So minus would be your shifting right. So this would be we shift right 2 units. Or right 9 units, sorry. Now, last one. Think about this carefully. If we multiply a negative to our function, so in other words, think about our a value when we did a quadratic. What happened when I made that a value negative for a quadratic? It flipped the graph. So in other words, if the quadratic looked like this, it now looked like what if it flipped? So if I flip that quadratic, what does it look like? It's upside down. So in other words, I'm reflecting over which axis? The x-axis. So we reflect over x-axis. And that's exactly what this means. It means reflect it over x-axis. Now, why did I bring this up? Because this will help you a lot when you do some graphing. All right. So, first things first. If we start with our parent function, so all of these we're starting with our parent functions. So x squared, cube root of x, and x. Our new function is this. What transformation or transformations happened in example 1? So from the yellow to the green, what happened? The graph would shift right. How many units? 3 units. What about for the cubic graph? What transformations happened? So it shifted right 2. What else did it do? And it reflects over the x-axis or flips over x-axis. It's down 3. My bad. Because it's outside the radical. What about the last one? What's happening? Right. So it's shifting left what? So it shifts left 7 units and then does what? Up 9. So guys, what that means is that if you're just doing shifts, so if your functions look like that, where you're just reflecting, that's how you can graph it. If you know what the parent function looks like, that's how you can graph it fairly easily. Now, it's when you start throwing in dilations that it gets a wee bit dicey. All right. So remember, dilation, so whether it gets thinner or wider depends on any coefficient that's not a -1 being multiplied on the outside. So, all right. First off, besides the dilation, what other transformations are happening? All right. So it's going up 5 and then what? Right 1 and then what? And then it'll reflect over x. All right. So I'm going to start by graphing our parent function. I'm going to do that in black. All right. So it's a square root function. So that means 0, 1, 1, 4, 2, 8, 3. Just so I have something to reference. So again, this is my parent function. Yeah, it's 9, 3. Oops. Still similar shape. All right. Now, I am then going to do some transformations. Now, so I'm going to do the reflection first. So if I do the reflection, all right, the 0, 0 will stay where it is. Where would the 1, 1 point be now? 1, -1. So we just count how many away from the x-axis it is, go the same distance on the other side. So this would be after I reflect over x axis. Now, next, I would have to deal with the dilation. So, would the dilation affect my x value or my y value? Think about this carefully. Is this 2 being multiplied to the x? No, it's being multiplied to the entire function. So what would it affect? The y's. All right, it only affects the y's. So I'm going to multiply each y value by 2. Not -2, 2, because we already did the reflections. We don't need to worry about it. So, still out here. What's -1 times 2? -2. So the x value is still the same, but that's my new y value. What's -2 times 2? -4. So that's my new y value. What's 3 times -3 times 2? -6. So this would be when I do 2 times f of x, or the dilation. So I start with my parent function. I then did the reflection, and then I did the dilation. All right, we're still not in my final graph. My last one, I'm going to do my shifts. So from the blue graph, all right, I'm going to shift right 1 and then up 5 for all of them. So at 0, 0, I'm going to shift right 1, up 1, 2, 3, 4, 5. For my second point, I'm going to shift right 1, up 5. Oops, wrong point. Right 1, up 5. So 1, 2, 3, 4, 5. My next blue point, I'm going to go right 1, up 5. So this would be right here. And then the last one, I go right 1 and then up 5. So be at -1. So this would be my final graph. So this is after I did the shifts. Yes. So we're doing this in steps. The parent's function is where you started. So this is where you start. My first step was the reflection. My second step was the dilation. My third step is the shift. And that's always the order you want to go in if you want to do it that way. So this would be my final graph of the function. So the highlight is my actual graph of the function. Now, that's a lot of work. You could have just done that by using a table. So in other words, just take values from your parent function originally and just plug them in for x. All right. So in other words, if I did all of my parent x values, so 0, 1, 4, and 9, I just plug them in. 0 minus 1 is -1. All right. So that wouldn't work. So I'd actually have to start with 1. So in other words, you're looking for values that if you subtract 1 to, it would actually give you perfect squares. All right, so in reality, what you'll find is that it's actually your x values here. So your new x values would be 1, 2, 5, and 10. And then your y values would match up after you put them in. Because I based it off of what's under the radical. So another way you can think about it is whatever under the radical, set that equal to 0 and solve for x, and that's your lowest x value. So this is the lowest x value I can get. So I don't have imaginary. All right, any questions on that? But if you like doing it by transformations too, that's fine. Or you can just guess and check and plug in stuff for tables. It doesn't matter. All right. Let's do this last one, then we'll call it a day for today. All right. So let's just do this using a table. So instead of using the transformations, let's just use a table. So first off, given what's under my radical, so the x, what's my absolute lowest x value I can have? 0. Now, that means since there's nothing being added or subtracted to it, I can assume perfect squares. So I'm going to list my perfect squares of the rest of my x's. So 0, 1, 4, 9. Those are going to be my x's. So in other words, guys, you want your x values to be whatever numbers will give you perfect squares when you evaluate what's under the radical. So like over here, my perfect squares would be if I just subtract whatever number subtracted by 1 gives me a perfect square. 1 minus 1 is 0, 2 minus 1 is 1, 5 minus 1 is 4, 10 minus 1 is 9. Now, we're just going to, do the math. So what's the square root of 0? 0. What's 0 times 1/2? 0 minus 8, negative 8. Square root of 1 times 1/2. 1/2, or 0.5, minus 8, negative 7/2. Square root of 4, 2, divided by 1/2, or times 1/2, sorry. 1. 1 minus 8, negative 7. Then 9. 3. 3 times 1/2. 1.5 minus 8, negative 6.5. So this one would just be kind of a baby graph. So I have 0, negative 8, 1, negative 7.5, 4, negative 7, and 9, negative 6.5. So that's my graph. Now, one thing I did not mention for either of these. All right. Domain and range. What is my domain for the graph that I highlighted in yellow on the left? So what's my lowest x value? So look left to right. What's my lowest most x value? 1. And where does it go to? Infinity. Now, range. Think about this carefully. What's my lowest y value? Negative infinity. Because since this is pointing downwards. Where does it end? What's positive 5? What about on the over here? Lowest x. 0 goes to infinity. Lowest y. Negative 8 goes to infinity. You guys kind of see a pattern going on? If you notice it, their vertex, just like with a quadratic graph, kind of tells you where your domain and range is at. All right, we'll pick this up tomorrow. Your homework tonight, let's do
We need another day of learning before we have the capacity to.
Yeah, I'll let you work on the Delta math. I'll be nice. I'll be nice. I'll be nice. It's almost the holidays. Merry early Christmas. So you still got that Delta math though.